Let's see. Here. Okay. Don't know how to do this. Memoization. Nice. What's this one? Tabulation. Three pointers. Nah, I would leave. That's funny. How complicated is the first approach? Bro. What's the second approach? You tabulate. Third approach. I'm as disappointed as relieved that I would never come up with the editorial solution. Lord have mercy. Took 4 hours to solve this. Wallahi, I'm thankful to finally finish this problem. Oh, these are funny. I think I'm a GPT. Hopefully the GPT is right, but yeah, I saw it. I knew it was gonna be something like that. Oh, can you sort it now? That's crazy. Okay. I need to change my keyboards, bro. Oh my gosh. What's the editorial do? Oh my gosh, it does the same thing. Tabulation must be O of n. Is this faster? Sliding window. Okay. What? Oh. I don't like that. This makes a lot more sense to me. Jeez, bro. We actually need... I get why they do this now. What? This makes no sense. Like, these are not intuitive whatsoever. what? If this is the case, then probably max sum equals cur sum. Yeah. On the left, I equals I plus 1 minus k. I kind of get that. I don't even know why I do this. I should probably just do this. Copy and then just follow it. Because I'm literally just copying it at this point. Make sure it works too. Jeez. Yeah, okay. Prefix sum, max sum from the left, max sum from the right. Compute prefix sum. So this is what, a rolling sum? Yeah. So we calculate the rolling sum. So it'll be like 1, 3, 4, 6, 12, 19, 24, 26, 25. Max sum k minus sum 0. First subarray sum. This is too much, bro. What's the pass rate on this? Jeez, that's high. This is so complicated. Yeah, okay. I'm gonna save this for later. Because it's gonna take me like 2 hours just to get I'm sorry, not 2 hours. It would probably take me like an hour just to understand it. Let's go back here. There we go. It's just not worth like all the time and effort for such a niche problem that I most likely will never run into. Oh my gosh. This uses union find, I think. Yeah. This is just cycle detection, I think. So it's like you make a union find data structure with what? The number of nodes and the number of edges. I think it's the number of nodes. And for every edge, basically, okay, I should explain it. Basically, we just construct the graph and we run cycle detection on it. And if a cycle exists, then it's not a valid tree. Because then it's just a graph. And we're able to determine cycle detection with the union find data structure. Vertex 1 equals edge 1. Vertex 2 equals edge 1. So if union find v1 does not equal union find v2, union find.union v1 v2. Else, if they equal each other, then we're going to return false. And then the root is going to equal 0. Yeah, root 0. We're going to iterate through every node, and if the parent of the node does not equal root, we're going to return false as well, and then we'll return true. Yeah. So then we need to make the union find do we even need to do that? I don't think we do. Public int find int x. If the parent of x does not equal x, then we're going to return no, then this dot parent x equals find this dot parent x, and then we're going to return this dot parent x. And then we'll union I think you can do this dot. So if the roots do not equal each other, then if this dot rank root x is less than this dot rank root y, else if this dot rank root y is less than this dot rank root x, else. Okay, I need to think about this. Higher ranks are parents. So that means root y is the parent of root x. So dot parent of root x equals root y, and then this dot parent root y equals root x. Otherwise, this dot rank root y plus plus this dot rank root x plus plus this dot root y dot parent root y equals root x. Yeah, that's it. What? 41, 41, 41, 41. What? Oh, shoot. Looks like it's just returning false every time. Maybe we don't do this. One I. What am I doing wrong? It's probably here. This is also wrong. Okay. Oh. Is that it? Oh my gosh, that might be it. Missing edge count? Oh, whatever. I don't think that counts. Yeah, there we go. Unfortunately, all of these are union finds. Actually, I don't know how I'm gonna do this. So we're definitely gonna make a unified data structure. It'll be edges plus 1 rather than n, because n is just telling us the bounds of the node numbers, which isn't really helpful. I think the unified, we can. Yeah, so we'll make components be edges.length plus 1. Wait, no, it might be edges.length minus 1. 1, 2, 3, 4. Oh no, it'll just be edges.length. Sorry. Yeah. And we'll have a field in the unified data structure that tracks the components. It starts at edges.length, and then every time we make a union, we subtract. Every time we make a successful union, I think. Actually, this might be n. Because we need to be able to identify how many there are. Let's just try it. So something like that. Jeez. Okay, I need to change my... Yeah. There we go. I think here you do union find, and then when you find the, whenever the parents of the roots are the same, I think you can just return that. So union find what, +1, 3, I guess not. Oh my gosh. I think that's it. Yeah, there we go. It might get a few wrong, or not. This is absolutely terrible. I do not like this one. Basically, you iterate through each character, and then you iterate through each character, and you say, okay, if I change this to every other letter in the alphabet, does it exist in here? And then you topologically iterate through. You do BFS basically through this entire list until you can hit this. Yeah. So, one thing you can do is like make a set with strings in it, and then iterate through the word list, and then add the word into the set. And if the set does not contain the end word, we're gonna return what, 0? Yeah. And then otherwise, we are going to initialize a queue with strings, and then offer the begin word to the queue. And then while the queue is not empty, we get the current word, and then we get char array cur word, something like that, yeah. And then we iterate through every letter in the alphabet like so. And if, oh no, we take, sorry, we don't even do this. We iterate through each letter in the character. r.length, I++. Yeah. So we get a copy of the array. Actually, I don't know if we need to do that. Actually, yeah, we do. So for each letter and copy, we're going to set it to C. And then if we're going to make the new word, new string copy. If the set contains the new word, we're going to add it to the queue. And we will also remove it from the set. Or else we'll just infinitely iterate. Okay. And before that, if the new word equals the end word, we're going to return the counter, which will be before this, I can just say like, actually no, int counter. I think we'll do counter right here. Yeah. And then we're going to return counter. Oh, counter plus 1. I think this will be -1 too. You can't do this? You can do that with integer arrays, for sure. R.copy Java. I'm pretty sure that exists. .copy. Oh, copy of. I'm pretty sure. Can you char r equals blah blah blah. Oh shoot. Stop. Char r equals dot 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 r dot copy. Does this work? What? Bruh, that's so dumb. Does it work with int? I'm pretty sure it works with int. I've done it before with int. Okay. Ah, shoot, I messed up. How does this not work? Just turn A into C. C. Hmm. Oh my gosh. Oh shoot, I gotta pay a bill. I gotta do this first. Oh, I need to do it on my phone. Oh, thank God, actually. Because I can just run my phone on my laptop. Come on, work. Is it because I'm using it? I hope that's not the case. I'll just leave this here for now. Sure, let's disconnect. Beautiful. Let's go there. Bro, it should not be this hard. My bill. Bro, what? Oh, what a beauty. I love Apple sometimes. Pay. Oh, actually, I can just do this. Oh my gosh. I can just go here. Log me in. Oh my gosh, come on. Oh my gosh. Please work, please work. Oh my gosh, it worked. Okay, I'm gonna do this. Oh my gosh, come on. Come on, work. Beautiful. Okay. And then how do I reconnect? There we go. Reconnected. Oh my gosh, I love Apple. I just went on my phone through my laptop, or sorry, through my Mac, and I navigated through my phone on my Mac to grab like a digital credit card number, and then I used it to pay it off while streaming, while using my phone as my camera. That's kind of crazy. So what's wrong with this? Am I just supposed to break here? Like, why? I feel like it shouldn't do that. The second I start hippity hopping. Oh my gosh. There's no way. What am I doing wrong? I'm looking. Okay. Oh, I'm dumb. The whole reason why we copy. Oh, wait. It's definitely with how I'm doing this right now. So we can take what? Char, cur char. Cur char I. Do we have to do that? Yes, we do. That is awful. That is absolutely awful. So we go like int size here. And 4 in I equals 0. And then char r equals, no, it's like this. Yeah. R length. And then you do like char cur char equals ri. And then for char c equals a. C has to be less than or equal to z. C plus plus. Cur char equals c if string new word equals new string char or r if new word that equals and word to counter if set that contains new word, set that remove new word, q to offer new word. Well, r j equals c. I think I have to, yeah, something like that. And then rj equals cur char. Yeah. What? Oh, j. What the heck? That's why we're not polling enough. I think. Looks like it's broken again, jeez. This iteration method, man. Bro, what? Oh. Okay. I'm gonna redo that. That was a mess. Okay. That was not the most successful one. Let's do this. Priority queue. Okay, so what we'll do is we'll make a priority queue the size of k, and then we'll make it a min heap so it stores from least to greatest, and then as we encounter greater elements, we just pop and push. Yeah. So we have like public priority queue, injure queue, this dot priority queue, or this dot queue equals new priority queue, and then we'll make it size k, and then for int I equals 0, I has to be less than k, I plus plus, nums dot length, this dot add nums I. Wait, no. Oh yeah, that is it. So then if this dot priority or this dot queue dot size equals, we need to make like a public int size here. This dot size equals k is equal to size, then what are the constraints? Yeah, it doesn't matter. So let's do the not first. Actually, let's not do that. This might be wrong, actually. This is really messy. There's definitely a cleaner way to write this. Yeah, let's do some inversion. So, can we really? So if it fails the size, then we want to do that. Yeah, I think it actually works. You might run into some side effects. Yeah, see, this is a side effect. What did my old submissions have? How do we consolidate this code? Okay, so that size is less than this size. That makes sense. Oh, okay. Can't you technically do this then? Like if this dot q dot peak is less than val, this dot q dot poll, and then do like this dot q dot offer val, something like this. Would this work? Oh, if this dot q dot is empty, yeah, something like this. Technically, this is fewer lines, but logically, it's probably the same. Oh yeah, that doesn't work. Okay. Nice. This is the Smashing Stone ones. Oh. So we're going to make a priority queue, we're going to make a max heap, and then we're going to store all the stones in it, and then smash each stone as we go. And then if there's, smash each stone as long as there's more than one stone in the priority queue. And then the last value in the priority queue will be the return value. So we're going to initialize a priority queue, we're going to declare a priority queue, sorry. Priority queue. I'm going to make a max heap, and for stone and stones, queue.offer stone. And then while the queue.size is greater than 1, queue.offer, we're going to offer the queue a poll times, or no, minus a poll. And then we're going to return queue.peak. Queue dot is empty. Otherwise, there we go. N log n, n, so n log n. Closest points to origin. Oh, dude, these are complicated. So basically, we run distance formula. It's Manhattan distance, right? Oh no, Euclidean distance. What's that? Oh, this is, bro. It's actual like distance formula. It looks like. Yeah. So what we can do is we store all these values in the priority queue, and then we just make this calculation in the comparator for the priority queue, and then we will add all the points, and then we'll make an output array case size, and then pull as many as we can into the output array. So the real hard part is the declaration and not the declaration, but the initialization of the priority queue, because it's quite complex. So we have A and B, and we want to be able to store these values. So what do we want to do? We want to do A0 minus A1, and we're going to wrap this, and then math.pow this squared, and then we're going to add that to the same thing but with B. Wait, this is so dumb. I'll just do A0 times A0. I know. A0 minus A1 Actually, let's just undo that. I don't have to use math.pow, but I'm going to. And then we can wrap this in math.square root. Yeah. And then for each point, we're going to take the q and off for the point. And then our output array is going to equal k size. And for int I equals 0, I has to be less than k plus output I equals q.poll. And then we're going to return output. Yeah, but it's right here. That'll get rid of one of them, yeah. Okay, let's just redo this. Q and I don't like that. Wait, whoa, I'm dumb. It's just A0 times A0. How do I... Okay. There we go. Oh my gosh. What a mess. Alright, I need to go bathroom. Okay, largest element in an array. Isn't it a matter of like, so we're going to make a priority queue, set the size, and then it's kind of the same thing as the previous problem. I forgot the name of it, but if we violate the size, we're going to check if it's greater than. So we're going to store the 3 largest elements in a min heap. So sorted in increasing order. And then whenever we encounter larger numbers, we'll just add it into the heap. And then get rid of whatever's at the front of the priority queue. So we'll set a priority queue, make it integer, make it min heap, so natural is fine. And for every number in num, actually we need to set the size. Okay, if the size is less than k, then we just offer the number. Otherwise if q.peak is less than num, then q.poll and q.offer num. Return q, or return q.peak. Yeah, there we go. And log n. Size is going to be n. Kth largest element array. Task scheduler. Oh, this one's actually kind of hard. Is it? This one's pretty hard from what I remember. I don't think you use a priority queue for it. Yeah, there's like a mathematical calculation you can make, I think, to solve this. Yeah, you take the groups, you take the max group, something like that. I'm pretty sure. I'm not going to do this, but I'll write it down probably. Yeah, you take like all these calculations and then you can do it. I guess you have to sort in a way. I think this is the fastest way to do it. Yeah. Okay, I'm going to write this down because task scheduler, kind of difficult. It's like I'm starting all over again, bro. Design Twitter. This one's not too bad. Design Twitter is actually pretty cool. I like it. This is what interviews should be like. Okay. So tweets come in chronological order. So we're gonna have a public variable that keeps track of like the tweet ID, and it's just gonna be a simple incrementer. Start at 1 or start at 0, and then every time we make a new tweet, we just increment it once. So it's an ID system with a unique ID, and then we're going to make a user object, a tweet object. Users are going to store user IDs and a hash set of other user IDs that they follow. And then tweets are going to have a tweet ID and then tweet ID and their overall timestamp. So yeah, and then having all of that, we'll be able to do all of this. So if I make like int timestamp, we need this, right? So when we initialize Twitter, this dot timestamp equals 0. And then post tweet, get newsfeed, follow. Okay, so we'll need to make a user class and then a tweet class. Users are going to store public in user ID and public set integer following, a list of followings. User and user ID. This dot user ID equals user ID. And then tweet is gonna have something like int tweet ID, timestamp, and public tweet. We're gonna initialize tweet ID and timestamp. This dot tweet ID equals tweet ID. This dot timestamp equals timestamp. Okay. So I'm gonna do post tweet, follow, and unfollow first, and then I'll do get newsfeed last. So yeah, so when we post a tweet, the user ID and tweet ID. So we're also going to want a hash map of all the users by user ID. So we're going to store integer and user. We're going to call it users. This dot users equals new hash map. So if this dot users does not contain the user ID as a key, we're going to create the user. So this dot users dot put user ID new user user ID, and then we're gonna say we also need another instance field here of tweets. So this dot tweets equals new hash set. This dot following equals new hash set. So user equals this dot users dot get user ID user dot tweets dot add new tweet with tweet ID and this dot timestamp plus plus. So we're getting the user and we're adding a tweet to it. And then follow. So if this dot users dot contains key follower ID, if we don't have the follower, this dot users dot put follower ID new user follower ID. And then we're going to do the same thing with followee. This dot users dot contains key followee ID. This dot users dot put followee ID new user followee ID. And then user equals this dot users dot get follower ID. This dot users user dot following dot add this dot map dot get user this dot users dot get followee ID. I can make this simpler actually. Let's make this simpler. User follower equals this dot get this dot users dot get follower ID user followee equals this dot users dot get followee ID. Follower dot following dot add followee. Are we adding by it's integer? Yeah, we want this to be users. Okay. There we go. And then we're going to do the same thing with unfollow. So so unfollowing assumes that both of these users exist, right? So we also can make our lives easier by doing like public void create user. Actually, no, that won't make our lives that much easier. Unfollow. So user follower equals this dot users dot get follower user dot follow or user followee equals this dot users dot get followee follower dot following dot remove followee. Yeah, that's it. Okay, so we have all of these. And then we need to get the newsfeed. So this is when the priority queue comes into play. Actually, I think it'll be tweets. Equals new priority queue. AP. Most recent to least recent. So it'll be B dot timestamp minus A dot timestamp. Cool. And then we need to get the current user. Just .users.get user ID. So for each of my own tweets, the current user's tweets, we're going to offer it to the queue. And then for each user that I'm following, and for each tweet that following has, we're going to offer the tweet. And then we're going to iterate so while the queue is not empty, or int feed size. Feed size is less than 10. Oh no, wait, I'm dumb. While the queue is empty or the output size is less than 10, output.offer or output.add queue.poll, and then we'll return output. Feed size. Here we need to change it to tweets. No, tweet ID? Yeah. Variable follower might not have been initialized. Oh. I just said while Q is not empty. Oh, is it and? Yeah, it's and. There we go. We just made Twitter. Never mind. If this users does not contain the user ID key, then it will return feed. There's a lot of validation that needs to go on. Jeez. There we go. Find median from data stream. Okay. This is a little complicated. Find median. Okay. So we're going to have a lower and upper priority queue. The lower priority queue is going to be a min heap, and the upper priority queue is going to be that's a lie. The lower priority queue is going to be a max heap, and the upper priority queue is going to be a min heap. And we are going to, as we add numbers, we're going to make sure that the lower and upper are balanced. So one is not greater than the other by more than one. And then when we want to find median, we take the size of each of the lower and upper priority queues. If it's odd, then we grab the value from the odd or the greater priority queue. And then if it's even, then we take both values of the priority queue, both top values of the priority queue, and we calculate the median. So that looks something like this, where we do public priority queue, integer lower equals new priority. Oh wait, lower. Public priority queue integer upper. And then we say this dot lower equals new priority queue. We make this a max heap, and then this dot upper equals new priority queue, and we make this a min heap. We can leave it blank like this, but it looks weird, so I'm just gonna make sure that it's like that. And then when we add numbers, what we're gonna do is we're going to take this dot lower and append or offer the number, and then if this dot upper dot size is if this dot lower dot size is less than this dot upper dot size, I'm thinking about this weirdly. Wait. So if the lower priority queue is less than the size of the greater priority queue, then we're going to take this dot or we're going to take this dot lower and offer. This is really bad, actually. Okay, if this dot upper dot size is less than this dot lower dot size, this dot upper dot size is less than this dot lower dot size, we're taking this dot upper and we're offering this dot lower dot pull. And the reason why we need to do this first is because we want to be able to take the numbers, sort it within the lower half, and then we sort the upper half with the sorted number that we're pulling. So that's how we add the number. To find the median, if this dot upper dot size is greater than, if this dot lower dot size is less than this dot upper dot size, we're going to take this dot upper dot peak Otherwise, we're going to return double this dot lower dot peak plus this dot upper dot peak plus this dot upper dot peak, and we are going to divide. Actually, I'm done. We're going to return this dot lower dot peak plus this dot upper dot peak, and we're going to divide by 2.0. We should be good. Never mind. And it's breaking on the odd condition. Oh, I'm done. So if this dot lower dot peak is greater than this dot upper dot peak, we're going to take this dot upper dot offer this dot lower dot peak. Pole, not peak. I wonder what happens if I do this. How do we ensure that they're balanced? That's the problem here. Oh. There we go. Oops. I think we're good. I don't even want to think about this anymore. I think this is the way to go. No, it isn't. I can just say does not equal. I think that effectively does the same thing. Because lower will always be, if it's odd, lower is less. But this isn't working. Oh, that's probably why. What the heck? Oh, nice. What am I supposed to do? What am I supposed to do? What am I supposed to do? Lower dot size, upper dot size, upper dot peak. Oh, no, pole. Oh my gosh. I think I understand it now. Oh my gosh. Okay. Let's see. No, I don't understand it. Wait, what? How do I make this balanced? Oh my gosh. Come on, make it balanced. Lower. Let's just scratch this. Let's just scratch everything right now. So we're going to add lower. We're going to add lower. So if this dot lower dot size is greater than this dot upper dot size, this dot upper dot offer, this dot lower dot pull. Only when it's greater. So upper will always be equal to or one more than lower. So if this dot upper dot size is greater than this dot lower dot size, then we do this. Or not. I think I'm thinking about it the wrong way. I think it'll be easier if I do this. If this dot upper dot size equals this dot, or dang it, this dot upper dot size. Then we hit them with this, and then else is this. Because this is easier in terms of like the piecewise function, and it's still wrong. So we offer 1, lower has 1. So then we move it to upper. Did I get this wrong? Lower is a max heap. We want the max at the top. This is a min heap. We want the min at the top. Yeah, that makes sense. I think I have it flipped. We want to do upper first. So we want to do upper first because we want to assume that it's big. So we sort the upper. One, two, yeah. We always have to sort the top half first, I think. So if lower dot size is less than upper dot size, so it's still upper. So I hope this will help. It won't. This has to be lower. Yeah. I think that'll do. Never mind. Wow. I can't believe I'm actually messing up this badly. I see. Oh, this balances it. This balances it, and this makes sure that the lower is always equal to or one less. How does this work actually? Why do we need this? Because this ensures that it's balanced, but we don't know if it's an odd amount of numbers. We don't know which one has the median in it, because one of them has the median at the top, but lower dot size is less than. So it's 1, 1, 1. And then here it's 2, 2, 3. It's 3, 3, 2, 1, 2. 3, 3, 2, 3. This ensures that. Oh, I'm so dumb. It's because when you remove one from upper, I was thinking like, oh, you increment the size of lower by 1, but you also decrement the size of upper by 1. So there's a 2 size swing. So this ensures that lower will always be the greater of the two. That's why. Okay, I'm going to rewrite this one more time, and then we'll call it good for this session. Public priority queue, integer lower, public priority queue, integer upper. This dot lower equals new priority queue, a b minus a. This dot upper equals new priority queue, b a minus b. This dot lower dot offer num. This dot upper dot offer. This dot lower dot poll. If this dot this dot lower dot size is less than this dot upper dot size, this dot lower dot offer, this dot upper dot pull. And then if this dot lower dot size is greater, actually no, if this dot lower dot size equals this dot upper dot size, we're gonna return double. This actually no, we don't even need to do that. This dot lower dot size or dot peak plus this dot upper dot peak divided by 2.0. Else this dot return this dot lower dot. Technically, I can shorten the code by just doing this. Return this dot lower dot peak, something like that. Yeah. Oh my gosh. What am I doing wrong? What? What am I doing? Wait, what? Yeah. This is literally what I had before. What's wrong? What the heck? That was the whole point. Oh. Why did I do that? That was just a typo. Alright. There we go. Okay.